last tab on the docket today is the load combination tab. This is the same as the typical load combinations tab that you see in most of ENERCALC's modules. The load combinations are split into three categories. The strength load combinations, and in our case it is the ASD combinations. Then we have the combinations for reactions. This allows the user to control the combinations for reactions separately from the strength combinations. And finally, the deflection combinations. The user has a great level of flexibility regarding adding, modifying, or deleting combinations. Selecting certain combinations to be turned on or off, create combinations using opposite signs for wind and or seismic, among other granular control options. For this example, I will keep the combinations as they are. This concludes all of the required input information and we are ready to evaluate the results. However, before we do so, I always like to do a visual check of the main assembly. Let's click on the General tab on the left-hand side and then click on the 2D tab on the right-hand side. In the 2D sketch, I see the beam being W12 by 22, as well as the span being 24 feet, which both are correct. Then we click on the cross-section tab. I see that we have 6 feet effective width with a slab thickness of 3 inches, both of which are correct. Lastly, we click on the 3D tab and visually check the geometry. You can see that the total slab thickness is 5 inches. And again, the effective width is displayed as 6 feet. And we have a total of 24 feet for the beam span. I also check for the deck orientation. Currently, it's displayed as perpendicular to the beam. All of the 2D and 3D sketches are reflective of your input information. They also change dynamically in real time as you make changes. For example, if we change the deck from perpendicular to parallel, you can see that the 3D sketch automatically and immediately changes to show parallel conditions. Now that we have verified all of the input information, we are ready to evaluate the results. The maximum bending stress ratio as well as the maximum shear stress ratio are reported at the top, and both are under 1.0, which means the design is safe. Under the bending stress ratio, the results are further split into composite and pre-composite. Under the composite section, it shows you the composite action percentage, which is 25%. It also shows you the maximum applied moment as well as the maximum allowable composite moment capacities. Under the pre-composite section, you see the maximum applied moment as well as the maximum allowable moment capacity of the steel section alone. Next, we have a summary of deflection ratios. First, you have the maximum, total, and final deflection. This is the total deflection ratio when it's all said and done. ENERCALC also reports the load combination that produces the maximum deflection. Currently, the beam is slightly failing the deflection ratio limit, so we will come back to adjust that later. Then, you have the maximum deflection ratio for transient loads. You can check to see the load combination, and indeed this deflection ratio is produced by the live load. Lastly, ENERCALC reports the maximum pre-composite deflection ratio. This one uses whatever pre-composite loads we have, such as self-weight of beam, self-weight of slab, as well as any other construction loads or other loads that are applied to the steel beam before the concrete cures and achieves the composite action. Then, this load demand will be checked against the steel beam alone, aka using the moment of inertia of the steel beam alone. To get more granular deflection information, you can click on the Deflection tab. You can then pick the combination that you're interested in, such as pre-composite, total, or final composite, etc. This will display incremental results, such as the deflection along the length of the beam. You can also click on the Properties tab for more granular information, such as the location of the plastic neutral axis or the lower bound effective moment of inertia, etc. Now let's go back to adjust the beam so it passes the deflection ratio. You can do a variety of things to improve the beam's deflection ratio performance. For the purposes of this example, I am going to increase the composite action percentage from 25 to 50. This fixed the issue. The deflection ratio now is L/263, which meets the required criteria. Lastly, we need to check out how many studs we need to install. You can find a summary of the stud requirement under the Studs tab. From 0 to midspan, we will need 10 studs. Then, from the midspan to the end support, we will need another 10 studs. This means we can fit 1 stud per rib. If the design required more than 1 stud per rib, then the user will need to go back to adjust the QN capacity of the stud. Overall, the composite steel beam module is a powerful and versatile module that allows the users to perform their calculations and check different loading and section sizes quickly and easily. The rich and dynamic 2D and 3D graphics, as well as the various built-in design and analysis capabilities, make this module a favorite to many of our users. If you like to learn more or have any questions, you can visit our website, ENERCALC.com, or send us an email at support@enercalc.com. Thank you for watching.